This short lecture is intended to introduce you to the first mini-lab exercise that you'll be performing for this class. This is the mini-lab exercise called Kinematics. With respect to this mini-lab exercise, what you're going to have is a dynamics cart, this blue cart here. It's going to undergo a constant acceleration. What we are going to do is we are going to plot the position and the velocity of this cart as a function of time. We're going to use the velocity as a function of time as a means of measuring the acceleration. In order to ultimately obtain this data and analyze it, we're going to use a piece of equipment here that is known as a spark timer. What I want you to do is I want you to pause this lecture right now, and I want you to take a look at the short demonstration video called the spark timer or acceleration timer demonstration. Go ahead and pause this lecture and take a look at that demonstration now. Okay, now that you've seen that demonstration video, with the spark timer, you end up with a track, if you will, of the position of an object as a function of time. This shows up as the series of dots on the spark tape. Okay, what I'm going to do is I'm going to lead you through the process of analyzing the data on that spark tape. This process is common to a lot of the lab exercises that you'll see over the course of this year where we use an acceleration or a spark timer. Okay, so suffice it to say, when you do obtain data for this lab exercise, what you're going to see is the following. Okay, now right here is the spark tape itself. Because the spark timer has two prongs, it actually produces a pair of dots. However, I'm just going to draw one of those dots for clarity. For an object that is undergoing constant acceleration, you will see the spacing between the dots get progressively further and further apart. Now, right at the beginning of the tape, there may be a little bit of smear. This smear corresponds to the time when I turn on the timer prior to releasing the cart from rest. But then as soon as I do release the cart from rest, it then undergoes a constant acceleration. This then means that the dots will get progressively further and further apart, like so. Okay, now incidentally at this point, what you should probably do is pause this lecture and then go ahead and take a look at the short demonstration video that I've posted for you on obtaining data for this mini-lab exercise. Once again, this is the mini-lab exercise called Kinematics. So take a look at that short demonstration video now. This is how I obtain data. Okay, so now that you've seen the experiment performed, that now gives you a little bit of context then for what it is that I'm about to do here. Okay, so with my spark tape like so, what I then do close to the beginning of the tape is I choose a dot as my origin. Right here is my dot 0, and then I number out sequentially 1, 2, 3, 4, and so on, ultimately out to a dot 9. So this then means that I'm going to be working here with 10 total dots. The next thing to do is to construct our data table. And the data table is going to have a couple of columns associated with it, like so. And the first column is always labeled as the dot number. We use the letter N as an index to indicate the dot number. That is, N is equal to 0, N is equal to 1, N is equal to 2, and so on. So we have 0, 1, 2, 3, and so on, ultimately out to a dot 9. Okay, and then the next column is going to be the position at the nth dot. The position at the nth dot in terms of centimeters. Dot 0 is our origin. So then therefore for dots 1 through 9, using a ruler, what we then do is we measure the position of each dot relative to the origin. In other words, for dot 1, you measure from 0 to 1. For dot 2, you then measure from 0 to 2. For dot 3, you measure from 0 to 3, and so on. I have photographed for you the strip tape that I constructed for this lab exercise. You'll use that photograph that has a ruler held up to the tape in order to make these measurements for yourselves. You'll make the measurements of the position to the nearest ½ millimeter. The nearest ½ millimeter, that is in between the smallest tip marks on the ruler itself. However, you'll record your data in terms of centimeters. Okay, and then the next column is the time at the nth dot. This is in terms of seconds, where we start the clock at dot 0. Okay, now on the spark timer, it sparks 60 times per second. That's its frequency. Its frequency is 60 hertz. This then means that the time from one dot to the next is the reciprocal of that value. That is, it's 1/60th of a second. So the time at the first dot is 1/60th of a second. The time at the second dot is 2/60ths of a second, and so on, ultimately up to 9/60ths of a second. And then the last column is going to be a calculation. It's the velocity at the nth dot in terms of centimeters per second. Here's how we calculate the velocity at the nth dot. We're going to use the following formula. Take a moment to copy this formula down and let me explain to you how it works. This formula allows us to calculate the velocity at the nth dot. So for example, let's say that right here is my piece of strip tape, and right here is the dot in question, the nth dot. In order to calculate its velocity, we first of all take the following. We take the position of the dot ahead of it, the n+1 dot. So let's say that that's right here. And then we subtract from that the position of the dot behind it. That is the n-1 dot. That's this guy right here. So if you take a look at the numerator of the expression carefully, the position of this dot minus the position of this dot is actually just the distance between these two dots. And then the denominator of the expression is the time between these two dots. The time between these two dots is 2 times 1/60th of a second, or 2/60ths of a second. So notice that this formula kind of looks a little bit like an average velocity as opposed to an instantaneous velocity, because after all, it's just calculating the following. This distance here divided by the time between these two dots. However, through a long, laborious derivation that I'm not going to perform for you here in lecture, ultimately what we are in fact calculating here is an instantaneous velocity, the velocity at the nth dot. Now this sounds a little bit cryptic. However, using this expression is actually really easy. Here's the basic idea. Here's an example as to how we use it. Let's say that we're asked to calculate the velocity at the 6th dot. Well, what you then do is you take the position of the dot ahead of it, which is dot 7. And then you subtract from that the position of the dot behind it, which is dot 5. And then you're always dividing by the same quantity, the time from this dot to this dot, which is 2 times 1/60th of a second, or 2/60ths of a second. Like so. You'll notice, however, that you can actually shortcut this calculation a little bit, because taking the quantity here in the numerator and dividing it by 2/60ths of a second is actually the same thing as just taking the numerator of the expression and multiplying it by 30. That is, it's the same thing as this. Like so. Notice that you can't use this formula, however, for dot 0. And the reason for that is we don't have a dot -1. So then therefore, in other words, you have to start somewhere. This then means that on the data table, you put a slash here for the velocity at dot 0. Similarly for dot 9, there is no dot 10. In other words, you have to stop somewhere. So then therefore, you can't use the formula to find the velocity at dot 9. So then therefore, also on your data table for dot 9, you put a slash here for the velocity like so. So you use this little formula to find the velocity for dots 1 through 8. We'll use this formula consistently throughout this course when using these spark timers to ultimately describe motion under an acceleration. Okay, and now, once you have these velocities calculated, specific then to this mini lab exercise, you're going to be doing the following. On the first piece of provided graph paper for you in the mini lab exercise, what you're going to do is you're going to plot the position as a function of time. Now, when you scale your time axis, by the way, don't convert these fractions here into decimals. Instead, go ahead and write down the fractions themselves, because this then makes it easy for you to scale this axis. So for example, you would say skip a space, 1/60th of a second, skip a space, 2/60ths of a second, and so on like so. And then you will have to figure out how to scale your vertical axis here for the position based upon the measurements that you make from the photograph. Once you have then scaled that axis, you then plot the points of the position as a function of time. Now recall that the position as a function of time for an object undergoing one-dimensional motion with constant acceleration is of course described by this equation. Notice that it's a quadratic. This then means that when you graph out position as a function of time, very noticeably what you should see is a parabola. Now the vertex of the parabola will not necessarily be at the origin. The reason for that is because the object is already moving when we start keeping track of it at dot zero. However, the points that you plot should be very noticeably parabolic. It should look, in other words, something that kind of starts to look like this. Just seeing this general trend, in other words, the parabola itself, is all that we're after for this portion of the lab exercise. You don't have to connect the points. You don't have to draw the parabola itself. But it should be noticeably parabolic when you plot the position as a function of time. And then the second graph that you're going to construct is the velocity as a function of time, and then we will specifically use that graph to measure the acceleration. Here's how that's done. Okay, so now for the second graph, you're plotting velocity in terms of centimeters per second as a function of the time t in terms of seconds. Once again, scale the time axis by using these fractions. That is 0, skip a space, 1/60th of a second, skip a space, 2/60ths of a second, and so on. And now when graphing the velocity as a function of time, based upon what it is that you calculated, you'll have to use those calculations to scale your axis here. You don't necessarily, by the way, have to start here at the bottom with a velocity of 0. You could instead use what is called a break at this portion of the graph. That is fine. Now, when we graph out velocity as a function of time for an object undergoing one-dimensional motion with constant acceleration, what you should see is something that is linear, and the slope of the line is specifically the acceleration a. So here's then about what you should obtain when you graph out the velocity as a function of time. Your points should basically look something like this. It will very noticeably be a line. It will very noticeably be linear. What you then do is you take a ruler and you draw what is simply referred to as a best fit line. That is good enough for our purposes when doing these laboratory exercises. So what you then do is you take your ruler, you kind of hold it up to your points like so, and you try to get as many of the points as close to the ruler's edge as possible. And then what you do is you draw a best fit line. That's perfectly fine for our purposes. And then you pick 2 points that are on the line in order to calculate the slope. They could be 2 of your data points. However, you could also use corners, for example, on your piece of graph paper in order to obtain an ordered pair. So for example, let's say that I happen to use this point here, say, which does hit my line, and say this point here, like so. If I have the ordered pairs of these 2 points, then I can easily go ahead and calculate the slope as rise over run. Recall, of course, that the rise is the distance between the y-coordinates, if you will, of your ordered pair. That corresponds to the vertical axis. And then the run, which is this distance here, that then corresponds as the difference between the x-coordinates in your ordered pair. That corresponds to this axis here. So rise over run, that of course is the slope. This is the acceleration a, and it's in terms of centimeters per second squared. Now, even though I'm describing everything here specific to this mini lab exercise, once again, whenever we do a problem or a lab situation involving a spark timer with constant acceleration, we always find the acceleration by using this procedure. We calculate the velocities here as a function of time, and we then plot velocity as a function of time, obtain the slope of the line, which is the acceleration A. Follow the remainder of the directions that I have posted for you for this mini lab exercise when you now begin to complete this mini lab exercise.